Okay, so for our first example here, we have this function. It's in the back of the first page of the packet. P of x equals 2x cubed minus x squared minus 12x minus 9. And we're asked to use the rational zeros theorem to identify the possible zeros, then test them using synthetic division. Okay, once we do that, now if we can get one of these potential zeros to work, we're going to be left with a quadratic. If we're left with a quadratic, we can just factor it to find the rest of the zeros. Okay, so if you have a cubic, you're only going to have to find one. I think our second example today, we have a fourth degree, so you have to find two zeros for more work. So with this, remember that for our possible rational zeros, we looked at the number which we call lowercase p, which would be the factors of the constant term, right? So that would be factors of 9. So that would be 1, 3, and 9. You all remember this from yesterday, the day before. And then q would be the factors of the leading coefficients, so that would be 1 and 2. And then we know that our possible rational zeros would be plus or minus, because we have to consider positive and negative. With this, we're going to take each of these, so we'll do 1 over 1, which is just 1. 3 over 1, 9 over 1, so that will give us 3 numbers there. And then we'll do 1 over 2, 3 over 2, and 9 over 2. So altogether, we actually have 12 possible rational zeros, right? Because you have the positive and the negative. And what this means is that if there is a rational zero, it'll be in this list, right? Every rational zero is contained in this list. Now, there's no guarantee there's a rational zero. There could be irrational zeros, things with like square roots or things of that sort. There could be complex zeros that have i's in them. But if there's a rational zero, it's going to be in this list. So what we're going to do to find one of these is we're going to just start with our list and just got to pick one and just try synthetic division. Okay, what we're looking for here is we want to get, when the remainder is 0, then we know that it's a 0 of the function, and we know there's an associated factor. Okay, so to start with, I usually start with the positives just because it's easier to add stuff together, kind of. So we'll get 2, -1, -12, -9. Now, to be honest, I didn't even bother doing this one on my paper, because if I look at it, if you just look at the coefficients, if you're putting 1 in, we know it's going to be 2 minus 1 minus 12 minus 9, which is going to be not 0. But let's see what we would get. So 2 comes down, then we get a 1, get a 1, a -11, -11. That's not it, right? Doesn't work. So once I see it's not going to work, I usually just stop, because that's not what we're looking for. So let's go ahead and try 3. There's a nice rule. There's a bunch of rules that kind of tell you which ways to go and nice things to do and things to try. But we don't need to do a ton of them anymore. But the one I do like is if you put a positive number here in the box, if everything on bottom ends up being positive, right, so everything on the bottom row is positive, it means that no number bigger than that's going to work either. So say that if we're going to put 3 in, say if the bottom row is entirely positive, right, it means that 9's not going to work either, because it's just kind of a nice little handy trick. So let's try 3. Now I guess I could have finished this. It would have given us -20. It does tell you that on this curve we have the ordered pair 1, -20, because that is the output when you plug in. We don't really need to mark it or anything, but it's useful information at times. So here's 2, and then 6, and then 5, and then 15, and then 3, and then 9, and then 0. So that worked, correct? So what that tells us then is that p of x, our original polynomial, is x minus 3, 2x squared plus 5x plus 3. So again, I'm going to list the zeros because we were asked to do that, but I really, really like to sit on this factored form. Keep this factored form here. Try to get it completely factored. It has all the information you're going to need in it. So now with this, we just need to factor this 2x squared plus 5x plus 3, just to kind of walk through the steps of that. If you do 2x squared plus 5x plus 3, I always figured this is why your paper had margins, right? You could do additional factoring things. So we want two numbers that multiply to be 6 and that add to be 5, which would be 2 and 3. So 2x squared plus 2x plus 3x plus 3. Does that follow for everybody? Group them. So 2x, x plus 1, plus 3, x plus 1. We get 2x plus 3, x plus 1. So x minus 3, 2x plus 3, x plus 1. So that's the factorization. Now if you notice, the zeros that we get here, right, from this polynomial, we would set each of those factors equal to 0. We would get 3. We would get negative 3 halves. And we would get negative 1, which are all rational numbers, correct? Notice they all are in this list as well. 3, negative 3 halves, and negative 1. So just as we predicted, right, they're rational zeros. They had to occur in that list. So now at this point, we want to sketch the graph of the polynomial and state the end behavior and limit notation. So just a little review here. So we know the zeros, right, which give us the x-intercepts. We know the end behavior. We're going to write the limit as x approaches infinity of p of x equals, and the limit as x approaches negative infinity of p of x equals. And then what we do here is we know that this shape will look like this, correct? Because all the way back here, we have a positive leading coefficient, and we have an odd degree. So we're back to the same ideas that we had before. So this is positive, and that's negative infinity. Do be careful. This is, with limit notation, this is all you've just put equals infinity. You're just saying what the y value equals. You don't need to have a y over there. You really shouldn't, actually. So now in order to sketch this, we have these values. So we have a 0 at 3, at negative 1, and at negative 3 halves. We know we're starting low. We're finishing high. Do we see any multiplicities here? No, there's no multiplicities, right? So we're going to get something like that would be good. If you wanted to note down here would be negative 9. Because all the way back there are constant terms. So just a little bit of review, but this is what we're headed towards, right? We want to go ahead, we'll get our polynomial. We can use our rational zeros theorem to make a potential list. Then we start doing synthetic division to try to figure out what those are. It gets a little tedious sometimes. As you do more of them, though, you kind of get a feel for when they're maybe what's going to work, maybe what's not going to work. Like I mentioned here, just looking at it, I thought 1 was not going to work. Right? I predicted 1 wouldn't work. So I might have maybe even started with negative 1. And usually I run through the integers first before I start doing fractions. It makes it a little bit easier. Okay, so for our next example, we have this polynomial, f of x equals x to the 4th minus 2x cubed minus 9x squared plus 10x minus 24. Now this is a 4th degree polynomial, so most likely we're going to have to find 2 zeros to knock it down to a quadratic. Does that follow? So we're going to find 1 0 by having a synthetic division with the remainder of 0. Use that to factor it, and then we'll look at that remaining piece. So with this, the first thing we want to list is our p's and our q's. So once you list those, then we should be able to make a list of our possible rational zeros. So take a minute, try to list p and q, and see what we get. Okay, so as we look at this, our p's and q's, remember p's are going to be factors of 24, correct? Or negative 24. We're going to include positives and negatives anyway, so don't have to worry about that. Now what I like to do here, whenever I think of it, is I just start at the number 1. Does 1 go into 24? Sure, 1 goes into everything. It's not very Does 2 go into 24? Yep. Does 3? Yeah. 4? Yeah, it's kind of a stinky number, isn't it? 6? Yeah. 8? Yep. 12 and 24. And if you notice, 1 times 24 is 24. 2 times 12 is 24. 3 times 8 is 24. You should have pairs like that. You always actually have an even number of pairs unless it's a perfect square, which is kind of interesting. Now, Q's are nice here. It's just going to be 1. So our possible rational zeros, it looks like a lot of you had already started working on this, which is great. So what we want to do is we just need to test some of these. Again, I usually start with 1, work my way up, kind of see what happens. If I ever notice that when I'm trying one and it's not working and the whole bottom row is positive, I know it's time to switch over and start doing some negatives. So for 1, 1, -2, -9, 10, -24. Be very careful. I tend to struggle with these more often than I should because I write the number down wrong. I forget a negative sign. If you do that, the chances of having the right answer really decrease. So 1 will come down, and then -1, -10, -10, 0, 0, -24. Well, didn't work, but we know that there's a point. So let's try 2. I2, on these, you might even want to use separate paper. I would not erase the ones that you did. Some people erase them and leave them. That way, if there's a problem later, you can go back and check and see. So here we get 1, that's a 2, so 0, 0, -9, -18, -8, -16, -40. Well, I still see negatives on bottom, so I need to keep going. I think 3 might be or 3 or 4 works, I think. And we get 1, 3, 1, 3, -6, -18, -8, -24, 0. So that worked, correct? So that's good? Yes?
It was -24 plus -24.
Which doesn't work. Thank you. So it doesn't work. I was so excited, that whole negative thing. But yeah, it doesn't work. Does 4 work? Pretty sure 4 worked. Then we're getting close. Now, you might be thinking this is so much work, right? But we have a list of what? 16 numbers. Like that's a lot smaller than infinity. So this is the shortcut. It's not that short. So here we get 1, -2, -9, 10, -24. 2, 8, -1, -4, 6, 24, 0. That works. Right, so that works. So that tells us at this point we can rewrite our original function f of x as x minus 4. That's the factor associated with our original piece there. And then we have x cubed plus 2x squared minus x plus 6. Now we're not quite done yet because as we look, this is still a cubic. Now if you look at it, this is like a factor of 1 and 2, and this is 1 and 6. So it's not going to factor by grouping. But at this point, I'm going to divide the quotient here synthetically to find another 0, correct? So I don't want to go back to this list because if I look, the constant term here is just 6, right? So could 6 potentially work? Yeah, but I've already tried 1, 2, and 3. So I don't want to try 1, 2, and 3 again. Does that make sense there? And obviously, well, hopefully obviously, 8, 12, and 24 don't go into 6. So it wouldn't make any sense to try those. So once you get one to work, it does lower the list now. So for this, the possible rational zeros, because there's a 6 at the end of this, would be 1, 2, 3, and 6. Positive and negative. I don't think 6 works, because if you look, this would be positive, a positive number, and then 6 minus 6. So 6 is not going to work. And a lot of times you could think if I do plug it in, what would happen? Well, I get 0. So since 6 is probably not going to work, let's try -1. But now with this, we're not going to go back to the original. We're going to look at this quotient here. So we get 1, 2, -1, 6. So 1, -1, -2. That didn't do it. 2, 8. All right, so let's try -2. Right? So -2 could potentially work. Hope it does. 1, 2, -1, 6. So -2, 0, 0, -1. That didn't work either. Oh, almost there. -3 works. And then 2, 8. And let's try -3. You can see now why it's important to learn synthetic division, right? We wouldn't want to do this with long division. It's already a long enough process. So we get 1, and then -3, -1, 3 and 2, -6 and 0. So that does work. So at this point, and I need to go back over here, we'll get rid of this stuff. But what this gives us here is for our factorization for f of x, we have the factor from before, which was x minus 4. We have our new factor from here, which will give us x plus 3. And then we have the quotient here, which is x squared minus x plus 2. Okay, so we're almost factored, and now we have a quadratic, correct? So with the quadratic, we could try to factor it, but if you try to find two numbers that multiply to be 2 and add to be -1, you're going to be looking for a while because there's no integers that do that. So what this means is to find the zeros, we just have to set each of these equal to 0 and solve. Now these is obviously going to be 4, -3, but we can solve this one. So x squared minus x plus 2 equals 0. I'm going to use the quadratic formula. So that's -1 plus or minus -1 squared minus 4 times 1 times 2 over 2 times 1. You got to know the quadratic formula. If you need to go back to use some review stuff on the delta maths, that's fine, but that's in there. There's some review topics on that, but we should be able to evaluate these. So this is going to be, well, I guess I can't. Okay, so this is going to be 1 minus 8, correct? 1 minus 8. So we're going to get x equals -1 plus or minus the square root of -7 over 2. Now we don't leave a negative under the square root, we'll put an I on the outside. So this is a complex number, correct? So that's not going to show up on the graph at all. So we get x equals -1 plus or minus I radical 7 over 2. And then our zeros, we have this one, we had x equals 4, and we had x equals -3. So if we look, this is two numbers, correct? It's not the plus and the minus case. Yes?
Should the -1 be 1?
Oh, right here?
Yeah.
Yeah, it sure should be. Sorry. Whoops. So that should be a 1, right? Yeah, so the opposite of b, yeah, b squared. Everything else look good for this? Okay, so this is the process that we're doing. This is how you find the zeros. So we'd say this has two complex zeros. Well, actually all 4 are complex, but there's 2 that are truly complex and then 2 that are real numbers. These would show up on the graph. This would not. Okay, so that's where we're headed.